This is video 2 for the electrostatics unit notes. And in this one, we're going to talk about electric force and electric potential energy. So electrical forces, they result from the interaction of one object that has electric charge with another object that has an electric charge. So remember that if we have two charges that are opposite, they will be attracted to each other. If we have two charges that are similar or alike, they will repel each other. So what that means is that there must be a force that's either pulling them together or pushing them apart. Now, this electric force dominates the properties of objects in our everyday experience. The reason why we can stand is because there's an electrical repulsion between our feet and the floor. It's just that, a large number of particle interactions that occur all the time. We treat it in terms of everyday non-fundamental, like contact forces or normal forces or friction or tension. But all those forces, contact, normal, friction, tension, those are all the result of electrical forces. Electrical forces may be attractive or repulsive, and it just depends on the charges. So, something to remember is that a force is an interaction between two objects. So, when we talk about electric forces, there must be at least two charged objects. And then, again, opposite charges attract, like charges repel. Now, electric forces follow an inverse square law. So the electric force is proportional to 1 over the distance squared. We've seen this before when we talked about gravity. Gravitational forces are also proportional to 1 over the distance squared. And if you remember gravitational forces, we calculated them with our universal gravitational constant times m1, m2 divided by the distance between them squared, and then we multiply that by r hat to turn it into a vector. Well, we're going to see something very similar. The capital G was 6.674. Yeah, we got our universal gravitational constant found by Henry Cavendish. So that means then that for electrical forces, we're going to see something very similar. We're going to have a constant. We're going to have two charges, and they're separated by a distance squared. And we can turn this into a vector. This time, K is Coulomb's constant. And in this one, K is 9 billion. It's really large. And it's newtons meter squared per coulomb squared. Remember, the charge is measured with coulombs. All right, so let's use these models then to solve a problem here. So let's consider that we have 3-point charges at the corners of a triangle, all separated by 3, 4, and then 5 meters. Charge Q1. Now, the first thing I like to do when I look at these is I like to put positive or negative. So I see that Q1 is positive 6 coulombs. Then print it Q2 down here is negative 2 coulombs. And Q3 is a positive 5 coulombs. What we want to do is we want to find the force acting on charge Q1. Well, looking at this, Q1 and Q2 are oppositely charged. So if I'm looking at Q1, that means that there's a force that's attracting it to Q2. And I'll call that the force 2, 1. It's a force because of particle 2 acting on particle 1. Between Q1 and Q3, I see they're both positive, so they're going to repel each other. So there's going to be a force that pushes this way. I'm going to call this F3, 1. So looking at this, I can see then that the force acting on particle 1 must be somewhere in this direction and at this angle. So eventually I'm going to do some vector addition. All right, we'll go ahead and start calculating then. I'll start with F31. That's going to be K Q3 Q1 divided by, and then R is 3 comma 1. I got to square that. So that's going to be 9 billion times, now particle 3 had a charge of 5 coulombs. Particle 1 has a charge of 6 coulombs divided by a distance of 4 meters. And then I have to square that. So this will be 1.7 times 10 to the 10th newtons. And I see that's moving in the negative x direction. And then particle, or the force 2 comma 1, be K Q2 Q1 divided by the distance 2 1 squared. So that's 9 billion times Q2 is 2 coulombs, Q1 is still 6 coulombs. Distance between them is 3 meters. Remember to square that. So that's going to be 1.2 times 10 to the 10th newtons, and we see that it's moving in the negative y direction. So, looking at this information, I can see then that I have 1.7 times 10 to the 10th newtons in this direction. I'm just putting them head to tail. And then my force acting on particle 1, I just use the Pythagorean theorem and then inverse tangent. So this force acting on particle 1 will be 2.1 times 10 to the 10th newtons at an angle of 35 degrees, and I'll call it south of west. You could also call it below the negative x-axis if you wanted to. You can do any kind of thing that you want. That is electrical force. So very, very similar to gravitational forces. Now, electric potential energy. So first off, remember that the change in potential energy is equal to negative work, or I could say that work equals the negative change in potential energy. Work, then, so if I want to find the potential energy, I have to find the work. Work is the integral of the force vector dotted with the displacement vector. So, work equals the integral force vector dotted with the displacement vector. Okay, well, for electrical things then, the electric force then would be K Q1 Q2 divided by R squared. Dot product means that the force must be parallel with the displacement. And if I think about charges, the force would always be parallel with the displacement. It just would. And then the dx, well, that's going to become a dr, because in our problem here, r is our position, not x. R is like any kind of position you want. Okay, so I just need to evaluate that integral. Looking at this means that work, I can pull out all my constants. So K is a constant, Q1 is a constant, Q2 is a constant. So really I'm looking at the integral of 1 over r squared dr, which the integral of 1 over r squared is just 1 over r. So the amount of work is K Q1 Q2 over r. So in other words, if I wish to push two charged particles together, let's say they're both the same charge, I can use this formula to calculate how much energy would be needed to push those two charges together. So let's say they're both protons, and I want to push them, closer by 1 meter. I could calculate how much energy that would take. So The change in electric potential energy then would equal negative K Q1 Q2 divided by R. And again, this should look very, very similar because the change in gravitational potential energy was negative G M1 M2 over R. There's a lot of similarities between gravitational and electric. A lot of similarities. Okay, so something to remember then. Uh, a system with internal structure can have potential energy. So our system then would be the collection of charged objects. Potential energy then exists only within that system, and only if that system is interacting with conservative forces, which electric forces are conservative. So that means we can use conservation of energy with charges as well. The work done by a conservative force is independent of the path taken. The work description is used for forces external to the system. Potential energy then is used when the forces are internal. So remember, potential energy only works for a system, and conservation of energy only works within a system. Changes in the internal structure can result changes in the potential energy. So what this means right here, changes in the internal structure, if you move the charges around, that would change how much potential energy is stored within that system. This concludes video 2.